deadlock detection. You know what does it mean? If a system does not imply either a deadlock prevention or a deadlock avoidance algorithm, then a deadlock situation may occur. In this environment, the system may provide. See, in a deadlock situation, the system may provide some algorithms to detect the deadlock. An algorithm that examine the state of the system to determine whether a deadlock has occurred or not. It means the algorithm should run periodically to ensure that the system is in a deadlock situation or not. Ensuring means, of course, they will detect if there is deadlock, so their feedback will be that the system in a deadlock situation. If there's no deadlock, it means their feedback will be that the system is not in a deadlock situation. So, but who will ensure this? Algorithms. An algorithm to recover from the deadlock. So remember, once the deadlock detection algorithm detect that the deadlock is here, then the deadlock recovery algorithms will be initiated. Otherwise, they will not initiate, okay? Okay. So, allow system to enter deadlock state. It means that if the system is in a deadlock situation, then deadlock detection algorithm will be run. If the deadlock is found, then the recovery scheme will be initiated. Allow system doesn't mean that the intentionally we will allow them to enter a deadlock situation. It means that the situation will allow the system to go into a deadlock situation. Why? Maybe the system will be in unsafe state. Okay, that unsafe state will allow system to enter in a deadlock situation, and then deadlock detection algorithm will detect that. If found, then recover. As you know, dear students, we have two types of resources: single instance resource, multiple instance resource. For a single instance resource, to find the deadlock is available there or not, we will use another algorithm. And for the multiple instance source, we will use another algorithm. Okay. For single instance resource, we will use wait for graph algorithm or wait for graph to detect the deadlock. Here, nodes are called processes. The nodes in a wait for graph process are called what? Processes. Pi, Pj. If Pi is waiting for Pj, then deadlock is possible. You know what is Pi? Pi is a process. Pj is also a process. But Pj is a process which hold resources, okay? Which hold resources. Why we are using Pi and Pj? Because, you know, if we use P1 and P2, so that will be a kind of confusable. So instead of that, Pi and Pj, it means any process. Like for example, let's suppose there is a resource. Here's a Pj. Pj is holding this R1. But here Pi, one Pi, another Pi, all of them are waiting. Okay, so it means if it is 1 or if it is 2, both of them will be represented by which P? By Pi. If Pj is 1 or Pj 2, how many P are there which is holding this resource will be called Pj, okay? So Pj is a process which hold resources and Pi is a waiting process. It means that if in a graph we have such type of processes, then deadlock is there, okay? Which waiting. Okay, guys. So this waiting graph algorithm will periodically invoke, okay? It means that it will not run continuously, okay? it will periodically invoke. After a regular interval of time, it will invoke. Invoke mean run, okay? Periodically mean that, sorry. Periodically mean that after a predefined time, they will invoke and they will search for cycles. They will search for cycles in the graph. You know why they will search for cycle? Because the cycle will create a circular weight situation. A circular weight situation will cause deadlock. Okay, so they will search for that. And you know the circular weight will be there because of what? Because of this waiting and holding process. Okay, so if there is a cycle, there exists a deadlock, then there will be a deadlock. In this single wait for graph will report that deadlock is there. Okay guys, so let's try to understand this algorithm with the help of diagram. So this was the basic understanding about this wait for graph. First thing is that wait for graph is used for single instant resources, where wait for graph will be consist of Pi and Pj in multiple resources. And second, we will use n number of vertices. N number of vertices, okay? N number of vertices. Vertices, you know, vertices can be the resources and processes. Okay, guys. So we know this. This is our resource allocation graph. We already studied this in the previous lecture, that if you have single instant resources, in order to avoid deadlock, or in order to fairly allocate the resources, we will use resource allocation graph. Okay. Now we want to detect here, is the deadlock is here or not? So for that purpose, we have to shift to what? To this corresponding wait for graph. So this is what? This is wait for graph. Based on wait for graph, we can detect the deadlock in this resource allocation graph or in this algorithm. Okay guys, we know this. This is R2. R2 is holding by P1 because you know this is an assignment age. This is what? This is an assignment age. Here is, okay, let me change the color of assignment age by green. Okay, so this R2 is assigned to P1. R1 is assigned to P2. R3 is assigned to P5. And R4 is assigned to P3. R5 is assigned to P4. Okay, so all assignments is done. Now, let's find the waiting status, because as I told you that we will have two types of processes, Pi and Pj. So this P1 is a Pj, P5 is a Pj, P3 is a Pj, P4 is a Pj. Why? Because they are holding resources. Let's find the Pi. You know, dear students, that Pi is also, this P1 is also a Pi because it's waiting for R1, where P2 is waiting for R3 and also waiting for R4, because you know, this is a wait, this is a request age, okay? This is what? This is a request age. And the request age will represent what? Waiting. For example, if this side I have a process and this side I have a resource, so it means that this is a request age. And if I have this P1 and R1 and the age is to this side, then this is a assignment age. You know already these things, okay? Come back here. P2 is also waiting for R2. P3 is waiting for R2. You can see here, P2 is waiting for three resources. P3 is waiting, P2 is waiting for 3 resources, P2 is waiting for 1 resource, P4 is also waiting for 1 resource. So it means there is a lot of waiting situation. Okay, now come back to this. So I hope you guys understand this, the waiting and the holding situation. Based on the waiting and holding situation, we will draw this. Now in this wait for graph, you have to first eliminate the resources. Eliminate the resource and directly find it that P4 is waiting for what? For R2. When it will be released? It will be released by who? When it will be released by P1. So it means that P4 is waiting for P1 actually. That when P1 will release this R2, then I will hold that R2. So actually P4 is waiting for what? For P1. That when they will release the R2. So that's why I will draw the P4. P4 is waiting for P1. Let's find the P1 is waiting for who? P1 is waiting for P2 because P2 is holding the R1 and P1 is waiting for that. So P1 is waiting for P2. And let's know about the P2, that P2 is waiting for who? P2 is waiting for 2 processes, for P5 and for P3. P5, why? Because P5 holding R3. So it's waiting for P5. It's also waiting for P3 because P3 holding R4. And finally, P2 is also waiting for R5, where R5 is assigned to P4. So it's also waiting for that. And P2 is also waiting for P3. Yeah, we know this, that we all draw. P3 is waiting for who? P3 is waiting for P4. Why? Because R5 is holding by P4 and P3 is waiting that when this P4 will release this R5 and I will hold that. So that's why. So see here, I have 2 cycles here. Now I have 2 cycles. So the cycle number 1 and this cycle number 2. So it means deadlock is here, deadlock situation is available. So see, the waiting graph detect that deadlock is available in this system. Why? Because the processes are waiting for each other. The processes are waiting for each other and a circular shape is available, and based on that, this algorithm will report that the deadlock is available. Yeah, Ahmad Shakur, is according to you that why they are waiting for processes? Definitely, this is a wait for graph, and this wait for graph is developed based on this resource allocation graph. It means that this wait for graph is representing the status of this resource allocation graph. And we are determining that is here the deadlock is available or not. So now we determine and we confirm that there is 2 cycles, and based on that a deadlock will be available. Is it clear? Because in the wait for graph, we will not mention resources. Good. Let's continue. It's very easy, dear students, okay? If you know this logic that P4 is actually waiting for R2, and R2 is holding by who? By P1. So it means that P4 is waiting for P1, that when the P1 will release this. Just like let's suppose if Shakur is sitting on the chair in the class, there is 1 chair and Habib is arrived. So Habib will wait actually for Shakur, that when Shakur will free the chair, when they will stand and they will release the chair, then he will sit on the chair. So actually Habib is waiting for Shakur, that when Shakur will stand and they will release the chair. Same like that. Okay, so several instances of a resource type: available resource, allocation resource, request resource. These are some data structure, okay? We already know about these things. What is available resource? What is allocation resource? What is request resource? These are belongs to banker algorithm. Okay, the same things are here, but minor difference. Like now we are going to use the banker algorithm for the deadlock detection purpose. That's why you already familiar with these things. That work is equal to what? Available. Available mean available free resources which the system is hold. Work mean the same thing. And you also know that I mean what? The finished processes. Okay. And finished process will be false when what? When the resources will be not sufficient. Finished process will be true when a finish, I mean a process will be finished. It will be true when the resource will be sufficient. You know this condition that a finish I is equal to false. Why? Because request is less or equal to work, okay? And the finish process is okay true. When the finish process become true, then you have to re retake their resources, and their resources will be plused, okay, with the available resources, and the process will become true. If the process not become true, then go back to step number 2. Okay. If finish I is equal to false for some I, then 1 is less than or equal to I or less than or equal to n, then the system is in a deadlock state. It means what? It means that when this case is occur, the finish I is equal to false, then it means that for some of the I, the resources are not sufficient. One. Second, or maybe all those resources which are holding by the processes compare collectively, they are not sufficient for the waiting process to satisfy their request. That's why the system, the finish I is equal to false, and the system is in a deadlock situation. Okay. So moreover, if finish I is equal to false, then PI is in a which situation? Deadlock situation. So dear students, let's apply these things an example, and these things will make sense for us. So for this purpose, we will go back to our previous lecture example, and I will bring some changes here, and then we will see that the deadlock will occur. Do you remember this? Of course. Okay, so let me clear this. Okay, guys. So I'm removing some of the values. Okay, now I will increase some of these values. Like for example, it was 9, this time it will be 15. 15, 5, 7, 7, 8, 9. Okay, guys. Let's find first the need, that how much more resources are needed by these P0, P1, P2, P3, and P4. You know how to find this because we already studied the formula. The formula is what? Here is the formula that when you want to find the need resources, you have to apply this. need equal to maximum minus allocation. We have to maximize. We have to minus this the allocated resources from the maximum required resources. Okay. You know what is maximum? Because the maximum is the claim, as the claim resource. Okay. So this is the claim resource. Each process claim that I will need this much resources. This is the allocation, mean allocated resources. If someone is thinking that when the process is required this, claiming this 753 resources, that why the system is allocating 010? Because this is the algorithm. The algorithm will always keep the system in a safe state. So they will wait some of the resources and they will tell the process to have to wait. So allocation, because if you remember, we already studied their parameters that a process may wait or a process may have their all claim resources. Need mean we have to minus the allocation from claim to know that, okay, after some of the allocation, the system need how much more resources. Okay, guys? So for that purpose, I will go down and bring the table here to, or should I copy this here? No. Okay, guys. Just give me 1 minute. Okay, guys, so we want to find the need amount of resources, okay? So I am going to copy this table here. Good. Available resources mean the available amount of free resources with the system, okay? I think Khalid, you were absent in the previous lecture. See here, Khalid, these are the total instance of resource A, resource B, and resource C, where the system have 3 resources, A, B, C. A have 10 instance, B have 5 instance, C have 7 instance, okay? And this much instance are assigned to the processes from the resource A. You can see above A. So you have to minus these instances from the 7, from this 10, like 2, 3, 2 is equal to how much? 7. So 10 minus 7 is equal to 3. So 3 is here, okay? And same, you have to minus this from the B, from the C, okay? You will have 3 to 3, yeah, to this much resources, okay? Now come back to the table. Okay, guys, so the maximum resources for the A, B, C of P0 is how much? 753, yes, it's right. Then 722, yes. Now here we have some changes. It is 15, 5, and 7. P3 is 7, 8, 9. And it's the same. Okay, just we made changes in the P2 and P3, yes. So dear students, how much is allocated to P2? 302, yes. How much is more needed? 15 minus 3 is equal to 12. Okay, 0 minus 5 is equal to 5. 2 minus 7 is equal to 5. And here, 7 minus 2, okay, remember, you have to minus this from the 7, okay? and this 1 from this 8, because in this 1 from this 9. Okay, so 7 minus 2 is equal to 5. 1 minus 8 is equal to 7. 1 minus 9 is equal to 8. So this is the need amount of resources. Now I have to fill this need amount of resources. So dear students, 7, 4, 3. And then 1, 2, 2. No. 2, 2. Okay. Here 12, 5, what? 5, yeah, 5, 5. And the P3, I think, no, I'm right, okay. So 5, yes, 7 and 8. For the last process, which is P4, the need amount is 4, 3, 1, okay. Yeah, this thing is done. This thing is done. Now I have to cut and paste it again there, because I have to find some space for my other replace. Okay guys, so according to the condition number 1, need is less or equal to what? Work. If such cases become true, then the PI will be finish will be true. The PI finish will be true. Okay. Let's find this case. 3, 2. We have available 3, 2, 3, 3, and 2 resource. Okay. So the P1, 1, 2, 2 is 1, 2, 2 is less or equal to this or not? Yes, indeed. So according to that, the P1 will become true. Okay. So the P1 is become true and it's finished. What will happen after this? Work plus allocation. We have to retake the allocated resources from the P2 and we have to add them. So there is 2, 0, and 0. Okay. So the available resources are 3, 3, 2. Okay. We have to plus 2, 0, 0. Okay. So it's equal to 5, it's equal to 3, and it's equal to, yeah, it's equal to 2, because this is 2. So the available resource amount is increased. Now, 5, 3, and 2. Done. Again, the system will check the same condition. The system will check the same condition to know that whatever process is meeting this condition. 5, 3, 2. P1 is done. It's done. P4 is 4, 3, 1. 4, 3, 1. Is it meeting the condition? Yes. So let's handle this P3. No, not P4. Okay. Let's handle this P4. P4 condition has become true. P4. See, dear students, we are going to detect the deadlock. Okay. And after a few processes, you will see the deadlock is here. P1, P4 is done. And now I have to retake these resources. So 0 plus 0 plus 2. So it's equal to what? It's equal to 5, 3, and 4. Now the system have 5 instances of resource A, 3 instances of resource 3, 4 instances of resource C. Okay. Yeah, because the condition become true, meaning that the P1 and P4 is not in the deadlock. Based on what? Because the available resources is qualifying this condition. Okay, this need equal to needs less or equal to work. Based on this P1 and P4 is becoming true. Okay, Dries? Okay, now we have two true processes, P1 and P4. The system have 5, 3, 4 instances. So let's check this one. Yeah, I will check it for P2, dear. I will check it, okay? The system, the banker algorithm will first try to pick those processes which is meeting this condition very much. Why? Because the banker algorithm will try to collect more resources for the system, retake back the allocated resources to enrich the system resources. Okay, for that purpose, I will take the P2 and P3 at the end. Okay, guys, so now the system have 3, 5, and 4 instances. Good. So let's find that which, the P0. P0 is qualifying this? No. P1 is already done. P2? No. P2 cannot. P3, 5, 7? No. It's also not. See, now the system will be in a deadlock situation. The system will be in a deadlock situation for P0, for P2, for P3. Let's take the example of P0. You can see, dear students, P0 required 7, 4, and 3 instances. 7 from A, 4 from B, 3 from C. Where the system have how much? The system have 5, and here 3, and here 4. These two resources cannot match or cannot qualify this condition. So it means that P4 will be condition finish is equal to false. So here false is P0. Deadlock. See the P2. P2 is demanding for how much resources? P2 is demanding for, P2 is very heavy process, demanding for 15, for 5, and for 7. The system have how much? 5, 3, and 4. No, it's not qualify this condition. The condition is what? Now it's qualifying the deadlock condition. The deadlock condition was the opposite of this. When the need is less, or you can say the work is less than needed resources. Okay, let me come back to the slides. Okay, so now these conditions are qualifying, okay, because the condition is that resources are not sufficient. Why? Because of this. The I is demanding resources, and one is available resources. When the available resource is less or equal to what? To I, or I is equal, less than or equal to n. N mean what? The number of processes, okay, which I was waiting. So both things are becoming true here now. And that's why the the P0 is a deadlock situation, and now the P2 is demanding, as I told you before, 15, 5, 7, and the system have available 5, 3, 4. So it means the P2 is also in the deadlock situation. So P2 is in a deadlock situation because the Pi finish is equal to false for the P2. And let's know about the P3. P3 demand how much? 7, 8, 9. 7, 8, 9. The system have how much? 5, 3, 4. So you know that. Now what's going on? Now this condition become true. Work is less or equal to what? Need. Work is what? Work is this available resource. Need is what? Need is this. Where the need is greater than or, here the need is greater than what? the need is greater than available resources. You can also say that work is less than the needed amount of resources. So based on this condition become true, the finish I will be false. When the finish I is false, so we can say that the system is in a deadlock situation. Now the last process is P3. So dear students, we detect that the system is in a deadlock situation. Idris, now is it clear? Ahmad Shakur?
Yes, sir. Now I got it.
Very good. So we can say, dear students, that the system is in a which state? The system is in a deadlock situation. Why? Because our three processes, P0, P2, P3, their finish I is equal to false. It means that the need resources are greater than work. And now the system should think about the recovery because the deadlock is already confirmed. And now the system will take decision to recover the system from this deadlock situation.